right, welcome back everyone. So now we know how to put the color onto our triangles or inside of our triangles. But of course we do not only want to have triangles with a single color, but we also want to have some shade on them. So we want to do some shading to consider lighting conditions and so on. And we have already talked about this. This is actually just a one-to-one copy of a slide from the lecture on texture mapping, where we first started by talking about bilinear interpolation between color values on the vertices of a triangle. The only thing we didn't cover then is how to do this efficiently and how we deal with funk shading. And this is what we're going to talk about now. Good, and of course the answer to this is we use the scanline approach that we can use also. We have seen this, how we can use it for the set buffer, and in the same way we can use it of course also for interpolating the color values. We just need to calculate the delta RGB values. So we interpret here, we do not only look at the point, but we also look at the C, R, C, G, and CB value, the color values at this position here, and the color values, let's call this C1, and we can also call this C0, and I don't have to write everything. So we can use this scanline algorithm, or the approach that we use to, in a similar way, to calculate deltas between these values here, and then for each step we increase this by this delta, we increase the color value by this delta R or G or B. But of course also in between we want to do that, so we also have to calculate a value here, the 3 delta values here for these steps here in between these 2 points, and that way we can very easily and very efficiently bring color on our triangles. So we see here that we have to do 4 divisions to get the delta x, of course, first to get the intersection point, then 3 for the color values, plus of course 3 divisions in that direction for each scan line. So here we only have to do it once for each edge, and then times each scan line, of course. And also if we have a set buffer, we also have another division for this delta set, but we see that this is way more efficient than doing it for every single pixel, because we only have to do it for each triangle and not for each single pixel. Good. So yeah, this should be pretty simple and pretty straightforward, and this is then often called Gouraud shading, which is which models so-called diffuse lighting, which we had before in I think it was the 3rd lecture with our simplified shading model, where we called this the Lambertian shading. A lot of the stuff that I will discuss now is stuff that you should actually already know. I will do a lot of repetition now, so it will be quite boring for a lot of people, or actually I hope it is boring for you, because most of this you already heard, and also most importantly you have done it in the 2nd programming assignment. Nevertheless, I will go through it again, because first of all it is of course always important also to repeat stuff, and also not I mean, some of you split also the work in the programming assignment, so not everyone might have implemented that. Also, it is a good opportunity to repeat the mathematics, and also it's important for you, I think, to know, since like the practicals go a little beyond this, it's important to you to know what I expect to know from you in the exam, which is what I'm talking about here, and not what is covered in the practicals. The exam is the lectures and the tutorials, what is covered in the exam. Good. Yeah, so I will focus here a little more, like I said, more on the concepts. So the things might also be slightly different than when you do it in the actual implementation. I will stay much closer to the book. Unfortunately, the book is also not always very consistent with the naming. So for example, between this what I'm talking about now is covered in chapter 10. They use a different notation than they use in this simplified shading model in chapter 4-5, which is actually not that much more simple than what I'm talking about now. But so the different annotation, sometimes it can be annoying, but it actually can also be quite helpful sometimes for you if you look at compare the different notations and see how they really that they are indeed similar, or to see where exactly the difference is. If there is a slight difference, that can help you very often to learn it also. So when you learn about this, or when you read this chapter 10, I also recommend that you review the chapter 4.5, which is the simplified shading model. Good. Yeah, so the first one, Lambertian shading, we already said this. The Lambertian shading is the shading where we look into this diffuse lighting, where we have a matte surface and the light is reflected in a similar way everywhere, which means that the light depends mostly on the direction of the light, but not on the distance, for example, of the light. So but the direction influences it, and this has been verified by this so-called Lambert's or specified in this so-called Lambert's cosine law, which says that the color that we see at a point depends on the angle at which the light hits that particular point. So it is proportional to the cosine of that angle, which in turn leads to that is proportional to the scalar product between the two vectors of that form this angle, which are the normal vector and the vector L, the light vector, the light direction pointing from that point to the light. And you remember hopefully that the scalar product was defined as the cosine of theta times the length of one angle times the length of vector times the length of the other vector. That is the vector product of these two, is the scalar product of these two vectors. And if those vectors are unit vectors, then of course this value is 1, and then we have the cosine of theta is directly this scalar product. And so that means we can also, we do not have to calculate the angle, but we can also calculate the scalar product, which we can also do in a different way without this angle. And the important thing now, which I didn't mention talk much about at that time, because at that time we didn't have the transformation yet between the different the projection between the different the transformation between the coordinate system. We have to do these calculations in the world coordinates, because otherwise the normals will be transformed and will not be transformed appropriately. We already talked about that, but I didn't mention it explicitly that way. Yeah, so this way we can do this direction light, but like I said, it depends only on the direction. So there is no difference here if we have a light here or if we have a light here, which is of course why we sorry, I have some notes here that don't make sense. It confused me. I lost it. So start again. It only depends on the direction, which is why it's called a directional light, which is, for example, in contrast to a spotlight that you're supposed to implement as part of the third programming assignment, where, of course, if you have a spotlight, then from which position you're then the location is also important, because, of course, if you have a spotlight from the right or from the left, that can produce a different result. Good. Yeah, so for the Lambertian shading, we know it is proportional to the scalar product of these two vectors, and then we also know, of course, that it depends on the surface of the object. If we have a red object, it looks, of course, differently when we put light on it than if we have a blue object. But also it depends on the light. If we have a red light or a green light or white light, of course, that also creates a different perception of the object. So, and we do this by having these two factors here and multiplying the scalar product with these two factors here. And the other thing is that we have to consider is, of course, that the scalar product can get negative because it is proportional to the cosine, and the cosine is, of course, can get negative if the angle is larger than 90 degrees, which of course means that we're looking at it from the back. So we have to be careful that we deal with this, and this is usually modeled by just taking the maximum of 0 and the scalar product, which guarantees that the scalar product or that the result is always positive. So again, this is something that we already had. It's just a different notation here, which if you compare the two with each other should be should be obvious and should be clear. Good. Another thing Not sure if we talked about that, but that is, of course, when you do this diffuse lighting, you have to be careful how you do it on the vertices of surfaces or of models when you have them. So, for example, here for the cube, it is clear you have the normals on this side are like this, on this side they are like that, but here you have the vertex and you have two normals that point actually at an angle of 90 degrees of each other, so they are two different normals, so you have to decide what you do here. You could, for example, say I interpolate between the two and get a normal like this, or you could say I choose either or, and then have just the vertex the color of one of the sides of the cube. So this is a decision you have to make basically when you do the modeling. Likewise, so for example, for the cube, you would assume it's probably just the simplest way to just use a normal point, just one of the two normals, so just make one side a dominating side. Whereas if you have a cube, a circle, then of course you have normals pointing in this direction and normals pointing in this direction. So you could probably say, in this case, it kind of makes more sense to have an interpolated vector. I've drawn it larger now because otherwise you wouldn't be able to see it, but of course remember these are all should all then be unit vectors, so if you do an interpolation, make sure that the vectors afterwards are normalized. So an alternative approach that we could do, so this is, for example, if I draw it a little exaggerated, then we would have it like this here. And then we have an interpolated vector here, but that would of course cause here to have some intermediate mixture color between those two, and depending what kind of color this is, this could of course then end up in artifacts. So another thing you could do is, for example, to say, well, I just calculate this here and then I interpolate the normals here till I get to the next quarter, if we have something like that, and that way you get, yeah, this is horribly drawn, but I hope you get the idea. The idea is the same as we have it had with the bump mapping. So the point here is just you have to take care of it, and you have to do it in a specific way. And what is the best way is, of course, a decision you just have to make. There is no best decision. It depends on your models. For example, for the cube, very often just taking one of them is better. For the circle, you might want to do an interpolation. I want to mention this in a context. I read that in a book. I found it quite funny. In the first question of the FAQs that are usually at the end, there is the question, isn't this all? This all looks like a big hack, and the answer is, yeah, of course it is a hack. But it is a very efficient and a very the quality of it is very good. So I just want to use this to highlight that in graphics, a lot of time, especially when you're dealing with real-time graphics, when you want to use games, for example, and you have to really have real-time reaction, you very often use heuristics or hacks, depending on how you see it, because you have to make compromises, because we might have models that are describe this realistic or physical physics behind it way more appropriate than what we use here, but calculating them is not efficient enough to do it in real time, so we have to find a compromise. And very often in graphics you see some new algorithms which are kind of, yeah, look just like a hack, but they just produce very good results. We had this also, I mentioned this also in relation to the Perlin noise, but that is also why I'm always trying to also explain, not only just put the formulas there, but also try to explain how can we intuitively understand why this might actually produce good results. You have a question? Well, if you calculate it, and then you have a corner point. Well, at some point, if you have two vertices that come together, you have a connecting point, and if that is infinitely small, or if that is very small, it falls. At some point, you have to have a pixel where you say, at this pixel, these two segments end. And they come together. Otherwise, if you don't have that, you might have an empty space in between. So in any case, when we're drawing, we have to make a decision. There is a pixel, and this is the pixel where the segment ends. From the theory, you're right. From the calculation, you could argue in a way that it might be infinitely small, but here we're talking now about really drawing the pixel on the screen, and then you have to make a decision. This is the last one, period, and this is the one I draw. And then you have the situation that they meet in one pixel, otherwise you would have a gap in your model. And if they meet, then you have to decide what color do I put on this pixel. Good. All right. Yeah, another thing we already talked about is the global illumination, of course, because if we do it in this way, if we do model the light in this way, then we have the problem that objects that are not hit directly by light will be completely dark. That's how we defined our hack model. And so we use another hack to get the global illumination, which is basically the light that is always around us, which we said before. One option to do this is just to add a constant value, a constant color term to each object, which could be like the average of all the colors that we have in the room, because everything contributes to it. And then we have this one color term, and then of course if we do it, we have to be careful how to integrate it in our model, because you see here, if this is our constant color term that we add, we have these two other factors. The CR is the diffuse reflectance, which is the fraction of the light that is reflected by the surface, and that of course is also relevant for it's relevant for the original one, but it's also relevant for the ambient lighting, whereas this CL is the RGB intensity term that comes from the object, which is of course not which comes from the light, which is of course not relevant in this case for the ambient lighting, because the ambient lighting is, we put that in for the position where we don't have light. So this is why we don't multiply it here. Sorry, I got confused again. Another trick to do this, which we haven't talked about so far, is we can just put a dim light source at the eye position, because then we can guarantee that every point that we see has some light, because we are shooting out some light to that point. It's another trick to do it that is works also quite efficiently and quite well. Good. Now I assume you all know what's now coming. From the diffuse light, we go to the so-called specular reflection or glossy reflection, which is the reflection where we have these light spots here, because obviously the one how we discussed it right now, we didn't make any didn't make any differences between these different areas here. But if we have a glossy object, then of course we have these highlights here, which is then often also called Phong reflection, because the Phong reflection is the most, or the Phong shading model is the most popular model to calculate this. And the major difference, of course, between the diffuse shading is that the viewing direction in this case matters. So we said already that the reflection is maximized when the angle of the reflected light is the same as the angle of the incident light. So if this is our surface and this is then the light with the angle theta, and this is then the reflection at this angle here, the same angle theta here, is the maximum, and the more we move away from it, the lower the influence gets. So if we have an angle phi here, where we have our eye direction, where we're looking at the object, then the intensity of the reflection decreases if this angle phi increases. So again, we have something that is proportional to the size of the angle. So again, we can model this by using the scalar product of, in this case, the reflection vector and the eye vector, because that is the angle that if that increases, then also the reflection decreases. So this, and to do this, is called the Phong shading. But in in the practicals, or actually no, I think you are allowed to do both implementations. There is a variation of this, which is the so-called Blink-Fong model, where the only difference is basically that instead of using the scalar product, we're using here the so-called halfway vector in between the I and the light vector. The halfway vector is the vector that is exactly in between the light and the I vector, so we have the same angles on these two sides here. And then we can see, of course, the vector E is closest to this reflection vector if this vector H is closest to the normal vector, if it points directly in the same direction as the normal vector. So we see by taking the scalar product of n and h, we get the same relative result as we get here if we take the scalar product between E and R. And I'm saying the same relative result because the angle of the Phong shading, the angle of this so-called blind Phong shading, which uses this halfway vector, is always half of the vector of the Phong shading, which is why the result is a little different. And the difference is actually that we get a wider area here, but because we have this Phong exponent, which is just the here the exponent that we take that modifies here this value, we can also modify this in a way that by using a different Phong value, we can get almost the same result as with the blind Phong we can get almost the same result with the blind Phong shading than with the Phong shading. And the difference is, or the major advantage of this is with the Phong shading. I already said that we use the maximum because to avoid that we get into this area where we have negative values. I actually said something that's not completely correct. I said we get negative values if we are behind the object, but it could also happen that we get negative values if we are still in front of the object. For example, if we have a situation like this, that this is the light vector and this is the reflection vector, and wait, I have to make sure I draw this correctly. Yeah, then this here is, and this is 90 degree. Then if we are in this area, we get a negative value because the scalar product is depending on the cosine, which goes into below 0 by 90 degree. So if we are below 90 degree here, we get a negative value, although we are still in front of the object. So that would mean with the Phong shading we get a 0 here, whereas with the blind Phong shading, where we have this depending on the scalar product of n and h, then we have here, if you draw it with an example, you see that if this is our n, and no matter where we put the E and the L, we will not be able to create a case where they are both on this side of the object, but the H vector is becoming negative. So no matter how you construct it, the H will always be, or the scalar product will always be positive. Good. Yeah, and this is the Phong exponent, which I already explained. Now, the problem is, of course, the combination of the Phong shading with this interpolation that we talked about is, of course, that this interpolation does not consider the Phong shading. And one approach to deal with this is to instead of do the interpolation between the colors, we do the interpolation with the normal vectors, and this is like we already said it for the corners. Of course, that also influences here the values on the surface. So if, for example, we have a circle or a sphere, we have normals like this. Now if they are modeled with triangles, let's make an extreme case. We have something like this, and then of course we have normals like this. And of course we have to decide what we do on the vertex here, but also here this will lead to artifacts if we do the modeling with these normals. But what we could do is the same as we had with the bump mapping, we could do an interpolation between the normals in a way that we have here one, and then we have here, they move closely away till the center, till they're upright, and then in this direction. So, and this can then be done again by linear interpolation. And one approach to do this is with barycentric coordinates, and this is actually the major reason why I'm bringing this up here, because in the book they use a different notation for barycentric coordinates. And I also want to bring this because I saw in the exam a lot of people didn't even do the barycentric coordinates exercise, which was quite surprising for me, because I thought this is the one that is very simple and just straightforward to write down. But one of the TAs says, yeah, people are just scared about the name. I don't know. There's nothing scary about it. Even the difference between the notation I use in the book and the notation I use here is really simple if you look at it. In the book, they say the barycentric coordinates are defined as this. You have three vectors and multiply them with alpha, beta, and gamma. And what I did, I said we have three vectors and we multiply them, but only with two parameters. And the reason was that we used the barycentric coordinates to calculate intersections of a triangle and a line, or verify if the intersection point is within the triangle or not. And if you represent a triangle, then I think this representation is more intuitive, because it was the one vector n0 plus two, and then you have the two vectors which are the vertices of the triangle, and then the beta and gamma are just the values that you add here and here to get the linear interpolation of this vector on this plane that is defined by the triangle, which I found more intuitive when you do an intersection test of the triangles. If you do it for the interpolation, then I have to admit that this representation seems more, is at least to me, more intuitive, which is why I want to bring it now. It's if you take this here and then you just multiply beta n1, beta minus n0, then you see you have n minus beta n0. Yeah, and also if you do it here, oh wait, I got confused myself now. Yeah, if you reorder that, let's just write it down. If I get confused, then I should probably write it down. If you write this down, you have n0 plus or minus beta n0 plus beta n1 plus gamma n2 minus gamma n0. So you see here, if you group now the n0s, and then you get 1 minus beta minus gamma, which you just have to set your alpha, and then you see that these two representations are exactly the same. That also changes, of course, the condition we have for the triangle intersection, but most importantly, that makes it much more intuitively understandable that this is actually an interpolation between the three normals that we have. Good. And then again, of course, like we had it last time, only with a different notation now, which again, like I said, is just different letters used. We can combine all the three together into one model, and this time I even did not forget the function factor like I did last time. Good. And of course, we can also add multiple light sources, like I already indicated in the third lecture on this slide, and like you can do in the programming, in the third programming assignment. Good. Are there any questions about this? Yeah. Sorry, what? I don't know. I'm not. I don't do graphics programming myself, which is why for such questions, ask the teaching assistants. They can answer it. Good. Yeah. Any other question? Because then I'm already with my last slide. So like I said, today was basically a lecture where we wrapped up a lot of things. So because we actually have already now covered most of the basic stuff in the book. Actually, I think we have covered even more. I think we covered now chapter 1 till 11, and I think 10 and 11 are already listed as advanced topics. 10 was the shading that we just discussed, and 11 was the texture mapping, although I think it's a basic topic of graphics. We will not cover chapter 9, which is about signal processing. That is a little off in the book also. In the second edition, there was chapter 4, which was always, I found, a little off and didn't really fit into that very well. Now it's in chapter 9. It still doesn't fit very well. It's a very interesting chapter and it's very relevant, but it just doesn't fit to the other parts, which is why we don't cover it. Also, the third chapter, I already said this at the beginning, we're not covering that, only I mentioned the important parts every now and then. We will look now in the upcoming 2 lectures, or in the upcoming 3 lectures, into more ray tracing, which is a different approach than this perspective projection. I talked a little bit about this at the beginning. And the only thing that we will do now with the perspective projection approach is to talk about radiosity and shadows in the next lecture. And these are not in the textbooks, but I will give you the material for it. Good. Any questions? No? Then keep looking at this stupid watch. Then we are done for today.